me out. I am very happy to introduce to you Daniel Yahalomi. Daniel is a graduate student at Boulder University, doing his undergrad at MIT and a 2-year postdoc position on the test mission, which is the translating exoplanet to exoplanet. New exoplanets is the hot stuff right now. If you don't, you'll hear about it during this talk today. Daniel's research focuses on using a method of exoplanet perturbation known as transit timing variation. And today he's going to talk to us about what he's been working on for the past year. So thank you, Daniel.
All right. Well, thanks, Adina. I'm Daniel, as Adina said. I'm wearing a mask because I have a bit of a sore throat. I've tested negative twice for COVID, but out of abundance of caution, I'll do it. So people in the back can't hear me, just tell me, I'll yell a little bit louder. All right, yeah, so I'm a 4th-year grad student at Columbia. We're talking about some work that I've been doing with my advisor, David Kipping, as well as with David Naswuni here at SWRI and Eric Agel at University of Washington. Please interrupt, ask questions as we go. A lot of this is in progress, so I'm really excited about conversations. All right, so just to start, I'm going to jump in by having a little differentiation between parameter estimation and model selection. So parameter estimation, branch of statistics that involves using sample data to estimate parameters of a distribution, whereas model selection is the task of selecting a statistical model that best represents your data. So you can think of it as assume a model. Parameter estimation is assume a model, determine the best fit parameters, whereas model selection is determining the best fit model. And so that'll come up kind of throughout my talk. There's 2 different ways of approaching the science. Okay, so my research focuses on transit timing variations. To get to transit timing variations, you have to start with transiting exoplanets. So the idea of the transit signal, many of you maybe heard about it, but it's like a planet orbits a star. You're observing the time series photometry of the star. And so when the planet, represented by this blue dot here, passes in front of the star in a second here, in this bottom left figure, you'll see that the brightness decreases in the pixel level data on the bottom right, and as well as in the time series photometry. So that's what you'll see. These are the transits. And so that's what you'd expect if the only 2 objects in the universe were a planet and a star. Obviously, we know that's not the case in our solar system. There are 8 planets. A lot of the planets have moons or a lot of other interactions. And so you'd see that if a exoplanet transit for a single planet around a single star, you get that transit happening at the exact same time, very consistent orbital period, no variations. But once you add something else into the system, so here I'm plotting in red where you'd expect those transits may occur. If there's another gravitational effect in the system, you see that those transit timings vary or wobble. And so these wobbles we call transit timing variations or TTVs. And so what can cause these planets to wobble or appear to wobble? One way is multiple planets in the system. One way is a gravitational influence of a moon around that planet. One is stellar encounters, so binary star systems or stars that pass close by the system. And then planets can appear to wobble in the transit signal caused by stellar variability. Today I'm going to focus mostly on the multiple planets and the moon's case, because there are a lot of places where those 2 signals overlap and make it hard for model selection, but happy to talk more about the other 2 as well. Okay, so let's start with a brief history of planet-moon TTVs. So the first suggestion of looking for satellites via TTVs was in this paper in 1999 by Stark, Toretti, and Schneider. And a moon-planet TTV amplitude is proportional to the satellite-to-planet mass ratio multiplied by the semi-major axis of the moon's orbit. So the further the moon gets, the larger the signal, and the larger the moon gets, the larger the signal. And then these can vary from a realistic population from less than a second to up to an hour. But it can be difficult to detect moon-planet TTVs for 2 main reasons. One is the model selection question. It's hard to determine whether TTV is truly caused by a moon or by a planet or another cause. And secondly is that any moon, so within the Hill sphere, is where moons can live, will have an orbital period that's much less than the transiting period of the planet. And we only can sample TTVs once per transit. And so by definition, the sampling rate is the planetary period, which is greater than the true orbital period of the moon, which is equal to the TTV period of the moon signal. So we observe an alias of the true moon period. So that looks something like this. So you'd expect that if the moon TTV is this gray signal, we only observe at these black data points, so you observe this red alias. And so that makes it difficult to determine the true nature of the moon because you're only observing an alias of the true signal. You can take advantage of this aliasing effect and the fact that aliases are more likely to manifest near the Nyquist rate. So Nyquist rate is the minimum recoverable period based on the sampling rate, which is like 1/2 the minimum frequency or twice the, sorry, 1/2 the maximum frequency or twice the minimum period. So this is 2 times the period of the transitor. And in this paper in 2020, David Kipping showed that 50% of all exomoon-induced TTVs would fall between 2 to 4 times the transiting period. So this is kind of this stack up near this Nyquist rate. You can see that here. So in this white pie chart is where you'd expect aliased exomoon TTVs to fall. On the x-axis is the TTV period divided by the period of the planet, of the transiting planet. And then what you'll see is in yellow is all of the Kepler TTV planets. So Kepler was the predecessor to TESS. It launched in, I think, about 2008, observed the same area of the sky for 5 years. And there are several kind of great TTV catalogs with thousands of systems that show transit time variations. Now, what you'll see is that there's some overlap between the exomoon corridor and the Kepler TTV planets, but it seems like there's an offset in that the majority of the Kepler TTV planets don't induce these really short period signals.
Is that an observation or is that a theoretical statement?
The Kepler TTV planets is an observation. The alias exomoon is a theoretical statement. So in that paper,
why should we believe it?
Sure. Yeah. So in that paper, well, first of all, I think it's just a consequence of the aliasing effect. The Nyquist frequency, you expect to have a pileup near shorter periods. You're just going to recover the minimum alias signal that you can, and so you're more likely to get a stack up. And then the theory side of it is in this paper, David took like 4 different realistic exomoon populations. So one that was similar to solar system, one that was, I think, influenced by, or I think 2 that were influenced by different formation models, and then one that was more agnostic to what the moon population might look like. And in all of those cases, if you sample like a wide range of planetary parameters, you find that 50% fall right around this in this corridor, exomoon corridor. Okay, so then last year, or yeah, 2022, we did a search of the exomoon corridor in the Kepler TTVs to see if we could find any possible new moons. So we took these some 2,000 systems in this Hoaxer 2016 catalog, which sampled all of the Kepler planets that had at least 6 transits and looked for anything that had a periodic variation, transit timing variation. And our downsampling included things like removing false positives, removing any systems that are multi-planet systems, because we're interested in systems that are singles because they're more likely to be this TTV reduced by a moon. We made sure there weren't clustering effects that show the TTV, so the TTV signal was consistent amongst different segments of the data. Number of more statistical tests. This first gave us a set of 11 possible candidates, and then we further down selected those using another set of cuts, and we were left with our one best candidate, which was Kepler 1513b. It's a gas giant on a 160-day orbit. Because it's such a long orbit, 160 days, we only observed about 8 transits in the Kepler time data set. And so when you plot out, yes, the question naturally is this unseen companion to Kepler 1513 a planet or a moon? And if you plot what the Kepler TTVs look like, so let me walk you through what you're looking at. On the y-axis, the TTVs, on the x-axis is the transit epoch, the number, the transit number, basically. Yeah, the bottom half is the residuals, the top half is the actual TTVs. The black data points is our observation. Our red data point is the result of a planet-planet n-body model. And the blue solution is the result of a planet-moon n-body model. So you can see that both solutions could produce the observed signal. What we were able to do is observe 2 additional transit 9 years later. So both with tests and with ground-based observations. When we add those data points on our figure, you see that especially this 30th transit right here, if we map out where the planet model predicts the TTV to be, so versus the planet moon in blue versus the planet, you can't reproduce this multiple periodic component. And it's basically because of a planet moon TTV is very consistent with the sine wave. And so you can't have like this multiple periodic components. So you realize that's no moon. And essentially it's these 2 additional transits revealed a long-term TTV trend. And you can see that here we've done like a multiple component lomb-scargle reduction. So essentially what we do is we do a normal lomb-scargle fit to get the first peak amplitude, and then we take that peak period and run it back into a second periodic decomposition where we're now fitting for 2 sine waves, one on a standard lomb-scargle grid, and the other one optimized from being optimized but initialized at that peak value from the first lomb-scargle. And you find that we recover both the fast TTV, which is what was found in the original Kepler data, and then a slower long-term period. And so to understand what's going on here, let's take a step back and have a bit of a discussion about the history of planet-planet TTVs and the parameter estimation side. So the first recognition of planet-planet TTVs was in Dabrowski's and Barucki in 1996, followed shortly by Murata, Shkuda, and Schneider in the early 2000s. And there's some early papers showing essentially like what a linear ephemeris, it's basically a no transit timing model, looks versus data that with transit time variations on the top and the bottom what those TTVs might look like. And then in 2005, a set of papers pointed out the importance of orbits near mean motion resonance. So these resonances are planets with orbital periods close to integer number orbital ratios. So a period that's close to 2 to 1 or 2 to 3, or any integer combination. And so if a period ratio of planet P1 and P2 is within a few percentage of some integer ratio J to K, then the expected dominant TTV period is equal to this value, which is called the super period. And yeah, this is called the super period. And so we can plot out what we expect those TTV periods to look like. And basically you get this series of surface temps. This is plotting the expected log TTV period versus these resonant terms. And this is just using that super period equation. And you'll see in a later plot that popping up in n-body solutions as well. Okay, the second effect for planet-planet TTVs is this chopping effect. And essentially what was presented is that there exists this degeneracy between the eccentricity and the mass ratios between the planets and the host star. And if planets are near mean motion resonance, the degeneracy can be broken, taking advantage of this chopping effect, which is essentially that at conjunctions, so when the planets pass each other, have their closest approach to each other, you have a very strong gravitational kick. And so you get this chopping effect for the period equal to the synodic period, which is the period of these conjunctions. And so you expect this to have a characteristic period of the synodic period. And this is just an example of what TTVs might look like using both this mean motion resonance term and the chopping induced by this conjunction effect. And so you see here, these systems both have period ratios of 1.52, so it's quite near the 3:2 mean motion resonance. In red, there's a higher eccentricity and a lower mass. And in green, there's a basic 0 eccentricity and a higher mass ratio. And you'll see that they mimic a similar signal, but you can break that degeneracy using this chopping effect, which here is this kind of short-term effect that you see in green more than you see in red. Okay, so just the main takeaway I'd say from that, we want to remember is that planet-planet TTVs have these two characteristic periods. There's the near mean motion resonance induced TTVs have the super period, and then junction induced TTVs have a characteristic period of the synodic period. Okay, so now why should we care about model selection of TTVs? If you look at the same Hoaxer 2016 catalog, and we've fit our own lomb-scargle periodogram to find any system to show a consistent period, and then we down select to only systems that have a big statistic that favors a periodic signal versus a flat line with a value greater than 10, so pretty high significance. We're left with 1,492 known TTV systems. Of these systems, only 794 are known to be in multis, which leaves us with about 700 planets that are not known multis. We only know about a single planet in the system, which means there's a lot of science to be discovered if we can learn how to differentiate between what's causing these wobbles. Yeah, so critically, as many of these, yeah, it's basically what I just said. But the solution is often degenerate, and we can get a sense of these degeneracies by using n-body code. So there's two main ones, Swift as well as TTVFast, and they're commonly used for planet-planet TTV parameter estimation. What we've done here is we took TTVFast and we simulated a set of two planet systems, all with two Earth mass planets. We varied the range of periods from, okay, so we say one planet is transiting, and then we vary the range of periods of the other planet from being 1/10 the orbital period of that planet to 10 times the orbital period of that planet. And then we fit a lomb-scargle to find that peak TTV period of the simulated transit data set. What we plotted here is the TTV period on the y-axis versus the orbital period ratios. And this should look familiar, similar to those mean motion resonance circus tents that we showed earlier. And I'm going to walk through kind of what's causing these different effects. And I guess just to point out quickly, Kepler 13b and planet C likely live here. So these are the two orbital periods you recovered using the long-term trend. So we have this short-term effect, and then there's the longer period signal. But you could also see the issue is that you could find other places in orbital period space where you could potentially fit those two data points. So all we know is that the TTV period fall at those two dots or near those two dots. And so you could imagine shifting these along the x-axis and trying to find other locations in orbital period space where you could put another planet. And so this herein lies the problem. And so we've now been working to try to understand this orbital landscape, the period landscape of these TTV systems. And so to kind of walk through what's causing these different effects, the reason they all bounce back down here, that's just the Nyquist floor. So that's the 2 times orbital period of the planet. You'll never detect a TTV period faster than twice the period of the transiting planet. It's just the Nyquist rate. Here, I'll just plot where the excellent quarter expected to lie, so 2 to 4 times that transiting period. On the inside and the outside, you have the circus tents from the internal and external perturber near mean motion resonances. And then in here, you have this kind of chaotic region. And what's happening there is as you approach a period ratio of 1, mean motion resonances become so close to each other that they start to overlap. And so as the planets orbit each other, they get kicked into adjacent mean motion resonance terms. And so it's harder to predict what mean motion resonance would dominate in that system. And over time span of these 50 transits that we simulated, it's possible that they kind of jump into adjacent mean motion resonances. But when we plotted out these results, we found these 2 edges here, and we didn't know what was causing those. And we're kind of confused about why you have these, what looks like an additional edge, additional Nyquist floor. And so took a step back and tried to understand what's happening there. And we can explain it using another aliasing effect. So essentially here, you have to remember that we only observe planets during transit. So what did we can ask, what do the TTVs look like during transit? So if we put an observer here, we have two planets transiting a star. We'll say that the green planet is transiting, the blue planet's this external perturber. And here I'm just plotting what the chopping effect, the conjunction induced TTVs would look like, stopping at each time the inner planet, the green planet, transits. And as you'll see, as it walks by in time, even though there's a faster true TTV period, if the planet is far enough out, so here it's about 8 times the orbital period, you'll see that our observations carve out an alias that actually, by definition, equals the orbital period of this external perturber. And so here we have another aliasing effect that's affecting our ability to detect these TTV periods. And kind of plot it out all in once to maybe make this more understandable. You have, like, on the top half of the diagram, all 4 of the transits. The outer planet is pulling the inner planet through when it's transiting. So you expect an early TTV. And then on transit 6 through 9, it's in the opposite direction of when the transit's happening. So it's pulling the transit back, you're getting a late TTV. And so for these conjunction effect, if the period is greater than 2 times if the period of the perturber is greater than 2 times the period of the transitor, then the conjunctive TTV signal will be alias with a period equal to the perturber's period. So that explains this top edge here. But then what's happening with this second edge, what's causing this? And so to understand that, we can go from our conjunction-induced characteristic TTV period, and instead now look at our super period. And if you take our super period equation and divide through by J and K, you get this form of the equation. And what you'll see there is if we allow J to equal 1, so for a super period with a 1 to K mean motion resonance for periods P1 and P2, this equals a synodic period, so like this original conjunction TTV period, with a perturber at a period P2 over K. So basically what I'm saying here is this equation equals this equation if you allow J to go to 1 with a period P2 equal to P2 over K for the original conjunction effect. And so then a 1 to K mean motion resonant exoplanet edge has a period of P2 over K. And so we can explain this edge as the alias 1 to 2 mean motion resonant signal. And you can also see that manifesting because here's the 2 to 1 circus 10 as it hits Nyquist rate, it just bounces back and follows this line further periods. And yeah, I can explain more about why you expect to see those 2 edges and not the 3 to 1, 4 to 1, 5 to 1 for these low eccentricity systems after, or if someone wants to know now, I can say it now. All right, I'll continue.
Yeah,
Okay.
I was going to ask that. So why would you expect another line?
Yeah. So perhaps cheekily, we've started by just simulating low eccentricity systems. So these are just eccentricities between 0 and 0.1. And so when you induce higher eccentricity systems, higher order mean motion resonances are more likely to dominate. But at low eccentricities, you expect first order mean motion resonance, which means 1 to 2, 3 to 4, 4 to 5, 5 to 6 to dominate. And so theoretically, like the 3 to 1 mean motion resonance could have an edge effect. But this is the 3 to 1. This only hits a Nyquist rate at a value of a period ratio of 6. And at a period ratio of 6, it's far enough away from the 3 to 1 resonance that it's unlikely that the 3 to 1 is the dominant mean motion resonance term. You're more likely to be dominated by 6 to 1 or 5 to 1 or some lower order that's closer to that effect rather than being. And so for 4 to 1, you have to go all the way out to 8, 5 to 1, you have to go all the way out to 10. And so you're far enough away from that resonant term that you don't expect that that signal to dominate. Okay, so then you can ask, how do these edge predictions align with our current observations? And so we've taken the Hoaxer catalog for 2 planet systems where the period of the perturber is more than 4 times larger than the period of the transitor. And you'll see that there are like some maybe hints of clustering around these edges, but for the most part, there's a lot of points that don't fall along this edge, which is actually quite interesting because it implies that there's more mass in the system that we don't currently know about. So we know that there's 2 planets orbiting the star, but if the TTVs that we observed were induced by the planet that we knew about, we'd expect it to fall on one of these 2 edges. And the fact that it doesn't means that there's more mass, or perhaps a stellar activity signal that's causing this dominant TTV effect. And so there's more science to be learned from looking at deeper at these systems. Okay, so then I'll just end by saying what we're kind of working on now is instead of just fitting a single lomb-scargle, what if we fit 2 sine waves or multiple sine waves like we did for the Kepler 1513 system to this data set? So essentially you go from a TTV signal that looks like this. By fitting 2 sine waves, you can reproduce the majority of the signal. This is a signal that it has 2 dominant terms, so it does a good job with just 2. But for systems with higher order or more periodic components, you'd require more periodic components to explain it. And so I can just plot early on what happens if you plot both of those TTV periods, which is quite chaotic. But what's promising here is if you zoom in on one of the windows of these mean motion resonant terms. So here I've just looked at the 2-to-1 super period. So in black is our first peak periodic signal, and in red is that second peak. And what we're hoping to do is by building out this multiple periodic decomposition, predict if you see a certain number of TTV periods with a certain value set, we'll be able to hopefully uniquely predict where those 2 planet systems fall in order to cause these observed TTV periods. And so the way to think about it is like the fact that probabilistically, if you look at the set of like red peaks in this area, they're different when you look at other peak, black peaks. So if you look at the 2-to-1 set here, the red peaks are different there. The range of values is different than if you look at 1 to 2 internal. And so by using multiple periodic fits, we can hopefully break these degeneracies apart. Okay, so I'll just end with kind of the where we're at and where we hope to be. So again, we've been able to now explain what's causing these exoplanet edges for far-out perturbers. And we're hoping that this multiple component periodic decomposition can aid in determining a unique planet-planet solution for single transiting systems. Thanks, I'll take questions.
For the planet moon TTV stuff,
Mhm.
do you take into account eccentricity for either the planet or the moon?
Yeah.
Does it look like really clean sinusoids?
Yeah. So if you get really highly eccentric systems and the planet is accelerating because of the orbit, then it's not perfectly represented by a sine wave. In our actual fits, in our n-body code, we're fitting for that as well. But I think it's generally presumed, based on our current understanding, that sine wave does a pretty good job, at least for the moons in our solar system, the moons we know about. But yeah, when we fit for like the full n-body fit, we're allowing for eccentricity and stuff as well.
Yeah, so you talked about how TTV is still being used for stellar activity. Do you think it would be useful in the future to have some kind of large survey that has a different bandpass than test that could help remove that issue?
Yeah, so I think the more we know about our star's rotational period, the more helpful. So I could maybe go a bit into what's causing star. Yeah, so stellar activity induced TTVs, you basically, they can also be induced by stellar flares, but the most common cause of stellar activity induced TTVs we think are from star spots. And so there were a series of papers in the early 2010s that looked at star spot induced TTVs. Essentially, what happens with these figures are showing is if a planet, so yeah, in black is the planet, in gray is a star spot. And so if you have a prograde orbit, then when the planet passes in and the star spot passes in similarly, you'd expect at ingress to have a downward slope, which would cause a early fit TTV, early fit transit time. And then if it's happening at egress, you'd have a late fit. And either way, essentially, the solution is that TTV is induced by these star spots because the stellar rotation is what's causing the rotation, the period of these TTVs, is that you'd expect the TTV to have a period equal to the stellar rotation period or an alias of that stellar rotation period. So the more we know about the stellar rotation, the better we could rule out these false positives. I would look at it kind of like with the transit search in early Kepler days, there was development of these codes to do like false positive rejection. So we learned that like stellar activity could mimic a transit, but it would be more likely to be a V-shaped orbit. And so you could rule out transits that were V-shaped and call them stellar variability, or similarly for eclipsing binaries if there was varying depths. And so here it'd be if we find a TTV that is the same period or an alias of the period of the stellar rotation rate, you predict that to be a false positive by stellar activity.
Maybe this is a weird technical question, but what does a two-dimensional lomb-scargle look like? So
Yeah, so the way that we did it, so the way that it's been done in the past, that we've seen in the literature, is essentially you fit a lomb-scargle and then you subtract out that signal and then you fit another lomb-scargle. The issue there that we found is that you're basically assuming a perfect fit from a one-dimensional sine wave, and you can imagine for a very like chaotic signal, that sine wave isn't perfect, so then you're inducing extra noise into your second dimension. So what we did instead is we first fit a normal like one-dimensional lomb-scargle. We take that best fit solution for the period and the amplitude, and then we now create a model that's like has two sine wave components. For the first component, it's no longer linear because we are not stepping through a two-dimensional period grid. Instead, we optimize using like a least squares reduction initialized at the best fit parameters from the first fit. And then the second fit uses a standard periodic grid. And then we find the best solution there. And then similarly for a three-dimensional lomb-scargle, we have two now terms that are being optimized, and then a third is a periodic grid. And we can go up to higher iron orders that way and not fix a solution to a lower dimensional kind of decomposition. Yeah.
I know nothing about observing exoplanets. What is the like time resolution that you need to actually see this like TTV signal instead of just like a regular?
Yeah, time resolution in terms of like observational cadence.
Yeah.
Yeah. It depends how low you want to go. So Kepler, is Kepler's cadence minute, 2 minutes? You remember what Kepler's cadence is? 1 minute. So with Kepler, and I think in part because you have like 5 years of observations and a 1 minute cadence, you can get TTVs down to the order of minutes. If you have like a really clean data set, bigger transit, it's better. Yeah, so it depends how precise you want to get. Yeah. But I guess also the more transits you get, the more you fit the phase space. And I think the phase space is very important in determining what the transit time is, rather than the actual time space. It's the phase space. So when you overlay multiple transits on top of each other, so there's kind of a trade-off there. Yeah.
So for the one example, like the one Kepler object that you looked at and modeled in detail,
Yeah.
like the planet moon one was like a really clean sinusoid, and
Yeah.
the planet one was like pretty chunky.
Yeah.
Is that because of the kicks due to conjunction that you were talking about? Or-
Yeah, so there's a couple of things going on here. I'll go back here just so I can.
Yeah, I know it's like super early in your.
No,
talks.
you're good. Here, yeah. So I think a couple of things. I think first of all, we wanted to show the long-term trend, but the one thing I'll say is we don't actually have any information for what's happening in between each transit. So we don't actually think that there's a linear connection there. I just wanted to show in this plot that there's this overall trend, because we only have one observation for transit. So this is kind of done out, and the n-body plug will spit out where it expects the transit to be at each data point. So in reality, you'd expect it to be like a multiple component periodic. So it'd be like a sine wave with another sine wave put on top of it. For the moon, it's just much nicer because it very closely mimics a single sinusoid.
And then for your n-body work, like what's the setup and what's the assumption, or what are the assumptions that go into, like, is that a 2D simulation?
Yeah, for like the wide scale setup, like the when I'm showing the circus tent diagram, or what it specifically.
Yeah, like
I guess there are different assumptions for both. So like when we're modeling for this n-body fit for a planet-planet solution here, because we already know from the transit signal a good estimate of the planetary parameters for Kepler 1513b, we can set tighter priors on the range of realistic parameters for B, and then for C we adopt a really wide prior set. So any period from like, again, like a 10th to 10 times the orbital period. We don't really assume anything about the mass, anything about the eccentricity, anything about the inclination. We just kind of let it walk. We use multi-nest, so we use nested sampling, which is good at finding minimum when there's like a lot of local minima, and then converging in like a very degenerate set. And then for the like this simulation work, here we're doing we kind of just assume a wide prior set. So we use lower eccentricity because we know when you get to higher eccentricity you get more higher order super periods or mean motion resonances dominating. So this would be a more chaotic signal, and so as a first pass we're just kind of trying to target the low eccentricity regime. But for planetary masses here, we've done just Earth mass, but I've done the same thing with Jupiter mass objects, and you get essentially the same signal. The chaotic region looks a little bit different. It's more chaotic because the planets are more massive, and so you're more likely to kick into other resonances. But you know, here, like from 0.6 outward and from 1.5 outward, you get essentially the same effect, or the same peak periods come out. Cool. And then we've assumed we're agnostic on like the mean anomaly, mutual inclination within a reasonable range and stuff like that. Yeah.
I also have one question on this related to that. So this is generated pure side planets and low eccentricity.
Yeah.
Is that true of all those data points, do you think?
Yeah, so we have to look into more of that. That's a really good question. I think one red flag that perhaps these are could be just caused by two-planet systems is if any of them are really highly eccentric. I'd say for the majority of the Kepler data set, though, it would be surprising if a lot of them had higher eccentricities than 0.1, is my understanding. Yeah. But yeah, we definitely do need to look further before we start ruling that out. Yeah.
Thank you.